So good afternoon all. Again, we are going to start with strain energy of shafts under torsion. It's not different or difficult formula than the strain energy due to axial members, because we have seen the deformation of the twist are almost similarly related, right? The formula is the same. So therefore, strain energy formula is also going to be the same. Here we have the strain energy formula. So as if you can see on the right hand corner of the figure of the slide, right hand corner figure, you have here the twist in the member, and on the y-axis you have the torque given. So as you give on torque, your twist keep on increasing, and they will behave linearly as long as it is in the proportional limit, right? After proportional limit, it will go like flat, something like this. So as long as it is under proportional limit, it will remain straight. And the strain energy is the area within this curve. So it is area within this curve between phi and t. So that becomes half into phi a by 2. So half into t into phi. So that's your work done on the body. And the same thing goes as a strain energy in the body. Okay. So that's the energy that is kept within the body as shear strain energy. Now, if you replace t in terms of phi again, so you get gi by 2l phi square as your shear strain, right? So you see half comes here, and GIP by L into phi is your T, and then another phi comes. So that becomes your shear strain. And the formula, if you see, it's not very different from half P square L by 2AE. This is for axial member, remember, right? For axial member.
So there is one half extra here, right? In action.
Yeah, there is a half extra. Yes, right. I did so much, then now I have to. Okay, I just cut this one. So this is half into P square L by AE. So if you see, the relationships are very simple. So in place of P, you have to put T. Sorry. And in place of L remains L. So L is where the load is acting, right? And in place of A, you have IP. In place of E, you have G, right? And as we have done for axial members, we have found formulas for non-uniform sections or non-uniform. So there are a lot of torques applying at various cross sections. And if there is a non-uniformity in the material or non-uniformity in the cross sections, you use a summation formula here. Okay. And then there's an integral formula. Remember that this Ti is the internal stresses. Okay. These are the internal shear stresses. It's not the external shear stress that is applied. So I'll put a bar here if you want it to be. So that's how it is. T bar is internal. Shear stress, no internal force. Internal torque, that's better. Okay. Right. And let's do a small problem to see our understanding. So I have a member here, a shaft, and the shaft is acted upon by an external load at A, TA, okay, at B, at the boundary. Now there is another load that acts at the center, at point C, the same direction, not an issue, right? So for this, if I have to look at the strain, the twist will be from here and it will go like this till the end, right? It will be, twist will be something like this. So shear strain will act from A till B, and shear stress will also be from A till B. And therefore, its energy, strain energy is going to be half into TA whole square GIP into L, because 0 to L. But in this problem, if you look at the second problem, second figure, the load is acting at C. Therefore, from C to B, it is free to expand, right? So if it is free to expand from C to B, there is no tension, no strain that is acting here. The strain is only from here till here. So it will be something like this and then this. Okay. And since there is no strain that is acting here, there is no shear stress also acting there, right? The shear stress will be between this point and this point because this part is free to expand. So there is no shear stress there. All right. Okay. So up to this point, the member will have a twist like this. But after that, it will be a constant twist because there is no extra load that is acting there. Therefore, the strain energy is going to be up to L by 2 from 0 till L by 2. Okay. Now for a member where you have both together, what you have to do, you have to take cross section here, you have to take cross section here. So if you take cross section here, it's going to be only TA that is acting, right? So it is TA L by 2 whole square, TA square L by 2 into GP because this TA is acting till L by 2. But if you take a cross section here, it's going to be TA plus TB, right? So this cross section will have torque, internal torque as TA plus TB. So it's going to be TA plus TB whole square into L by 2 by 2G. And then you can add them up because both are in terms of GIP and L. So you can add them up and that will come out to be something like this. So this is on the whole section due to TA. This is on the whole section due to TB, right? And this is the combination of it. So the strain energies you cannot add up. You have to take sections and then add up. Okay. Now, if I give you this problem, a problem like this, see the lower part of the picture. So I give you a problem like this. Okay. And in that problem, it's a shaft of length L, let's say, and there is A point which is fixed, and there is B point where there is a torque that is applied. Okay. And I ask you, what will be the twist at C? How are you going to do it? Any ideas? Du by dt, yes, but after that, is that all or you have to do something more, Anikeswar?
So what does it mean? Like, I don't get your questions.
Yeah,
Like
is it only du by dt that you have to do?
No, so
du by dta.
it depends on the torque's position. So like where it acts. Like,
Torque is acting at B. I want you to find it at C. Okay.
So that we can use this relation as our like we have this. We can find angle twist. We can find strains and then use that to find angle
right.
twist.
Okay. Now I'm going to tell you another way of doing it. It is that you assume another fixed load acting at B, acting at C. Okay. Some fixed load, TB, let's call it a torque applying at that point. Now what I'll do, I'll find strain energy because due to both the loads. So both the load strain energy we have just found out, right? We just found out that it's going to be this one due to this part of the member and this one due to this part of the member. Now this part is due to both the loads, TA and TB. Remember, TB is still at fixed resistance load. Now, if you want to find a deformation at this point, you need to give a load here and take derivative with respect to the load at that point. Okay. So deformation at this point cannot be given by taking a derivative about this TA. You have to take derivative with respect to load at point C. Now, to take derivative with respect to load at point C, there was no load here. So we gave a fixed resistance load. So what we are going to do, phi of C is going to be del U by del TB. And then I'm going to put TB equal to 0 after we solve it because TB was not there initially. So that's going to be, you know, how to calculate this. It's going to be, this is independent of TB. So that's going to be 0. This is not independent of TB. Therefore, there will be something coming up. Now you put TB equal to 0, you get TAL by 2 GIP. Is that correct? Will that be correct? Yeah, right. It's correct because if I now do it, you know, through our formulas, analytical formulas. So I have this member and I have a TA here. So the torque is positive all through, and therefore I can find the strain directly by this. So T at B is going to be TA into L by GIP. And we know that this is linear, therefore that's going to be half. So that is TAL by 2 GIP. And this is also what we got, TAL by GIP. Okay. All right, so this method is called Castiglioni's method. We'll learn details of this method later, but you start using it from now itself because it's takes some time to get hang with this method. So what am I doing? I'll tell you again. So if I have a member and I've been asked to find stress at any other point, so this is the member and it is given by a load. It is loaded with a torque TA at B point. Okay, and I've been asked to find deformation at any other point. Okay, even if there are no loads acting at those points, I can find a deformation using Castiglioni's theorem. What it tells is the twist at any point that you want should be your strain energy, total strain energy of the member divided by, or not divided by, taking a derivative with respect to the torque at that point. Now, at point C, there was no torque in the beginning of the problem. So what we do, we assume some torque applying there, right? Now we have to find the total strain energy. Now total strain energy is not independent of this TB. It will include that TB also, right? So this becomes your total strain energy. The objective of Castiglione theorem is to take derivative with respect to the TB of the total strain energy. Now you do take that. Finally, since TB was not there on the actual problem, we put TB equal to 0. And that gives me this solution. Can you solve this problem? Solve this problem. Okay. What this problem tells? This problem tells that again the same shaft I have, but the load is at TC. Okay, load is at L by 2. So the torque is given at L by 2. And you have been asked to find the stress at phi B. Twist at B. Okay, use both the methods. So use strain energy method and use the formula also to find it. What you have to do in strain energy method, you have to assume a fixed load acting there. And then based on that, you will get your total strain energy coming out to be same again. And now what you have to do is you have to take derivative with respect to T acting at this point. So let's say if that is TA, then you have to take derivative with respect to TA, then you will get the formula coming out to be something different. So please do that and see what happens. And also do it based on the formula and check whether it's okay or not. Oh God. Yeah. So slides are visible, right? Hello?
Yes, sir.
Yes, sir.
Okay, fine. Thank you. Right, so let's go to the next problem. The next problem is we have again a rod, a shaft, and there is a UDL sort of thing. So uniformly distributed torque all through its surface. Okay, you have to first find how to find strain energy here, and then probably you can find the deformation at this point. So our twist at this point, we want to twist at point C, which is at L by 2. How do you do it? First, you have to find the strain energy of the problem. Now, I take a very small section. Now, for the small section dx, one side will be tx plus dx because load is changing, or the torque, external torque is changing. The other side will be tx. So this will be your internal torques, right? These are your internal torques. Now, tx is given as t into x. Constant intensity T per unit length. Okay. So how are we going to find strain energy of the problem? So strain energy for this small section is going to be Tx square. So I'll assume that it's almost constant within this small section. So Tx square then by 2 GIP and dx, right? So that is for this small section. Now for the whole cross section, I have to integrate between the whole length. So integrate between 0 and n. I do that integration, and once you do that integration, you can put what is this capital Tx. The capital Tx is going to be t into small x, small t into small x, because capital T is small t into small x. Okay, so any location you go, right? It's not t into x, it's only t, I think, right? Is loaded by a distributed torque of constant intensity t per unit length. Here it is t into dx, of course. So it is t into dx whole square by 2 gp. And then why tx is going inside?
Sir, I think it's per unit length. So they considered a length x and then multiplied it. Like for that length x, what is the torque they found? Sir? That is what tx is.
So that length is this dx. Not
So the
this.
small element is dx, sir. And at the end of the element x, there will be a torque acting tx. So that will be acting on the element dx. So like,
yeah, if the end of the point, if there is a torque acting tx, that means torque is linearly increasing. Oh, total torque acting is tx, sorry. Total torque, my mistake. So tx is the total torque acting at a distance x from pre-end. Okay, so I think you have done this in your BMDs and SFDs also. So if I take a cross section here, then that cross section will have t like that, and this is your x. So the external load that is acting here is t into internal load, that is the internal torque that is acting here, is t into x. Okay, because every portion will be balanced. So now if you put t into x within this integral sign, you get this is as your total strain energy of the member. What is our objective? Our objective is to find twist at this point. Right? How do I get twist at this point? I said that you have to take derivative with the load at that point. So at that point, there was no load, right? There was no twist, there was no torque that was applying. So I will put a separate torque at that point. Now I have to find strain energy due to both this torque as well as this distributed torque that is acting. So you can just do this. So up to this point, up to this 0 to L by 2, you have only tx whole square dx. But after that, it will be Tp plus Tx. So let us name it as Tp. So it will be Tp plus Tx. And you can do those integrations. Once you do those integrations, you can take derivative with respect to Tp and then put Tp equal to 0 to find the twist at L by 2. Do this at home. Okay. Do this at home. I'm adding a page here. You can do it. Right? Any question on that? Any question on Castigliano's theorem? In this case, your twist is not going to be linear, right? Can you tell me whether how the twist will be? Will it be linear?
No, sir.
It's not going to be linear. Yeah, it should be a second order something, right? So you have to draw, when you draw your twist, you have to draw it properly in that case. So do not make mistakes in drawing. Right, this is another member. This is another problem. Yes.
so small to the last question, sir.
Yes.
So for the same uniformly distributed torque, if you like for finding the twist at L by 2, sir, like you said, we can use that method also, like TP and
Castigliano's method.
Instead, why can't we just use the first term, sir? Like the first term 0 to L by 2 Tx squared dx by 2 GIP. Why can't we use that alone? Because we want to give the torque at L by 2 directly, like
You want to find a torque at L by 2. I want to find twist at L by 2.
Oh, sorry, sir. My bad. I'm sorry.
Okay.
Sorry, sir.
So to find twist at L by 2, I have to use Castigliano's theorem. So you find the total strain energy due to total torque that is acting on the system, and then take derivative with respect to load at that point. Okay, that's Castigliano's theorem. You can just Google it. So since there is no load, there is no point load at this point location, I have to provide a point load, and that's my point load. Now I will take derivative with respect to this point. Okay. Once I take derivative, since this point load was not there in the original problem, I'll put that point load after taking derivative to 0. And therefore, I will get my deformation or twist at that point. Another problem here, this is a tapered kind of rod. So cross-section is changing, and it has a diameter dB at fixed end and diameter dA at the free end. And there is a torque that is applying on the free end. We have to find its strain energy. Simple again, right? It's not difficult. You can do it in 2 ways. One is you can find strain energy that this solid portion, which is uniform, and then you can find strain energy due to this inclined portions. That's up to you how to do that. But let's say that I take a cross section somewhere, and that's my dA plus dB minus dA by L into X. So that's going to be my diameter at any section X from the free end. Okay, right? So the strain energy, and I will assume that this portion is small and constant. So therefore, that dx, I get my IP, or my polar moment of area, as that pi by 32 dx whole fourth at that portion. So the strain energy at that portion is going to be, and then dx is given by this formula. Strain energy at that portion is going to be then Tx whole square by 2I GPIX into dx, right? And then you can just integrate it from 0 to L. Okay. So now dx is IP, sorry, not dx. IP is this, IP of x. So IP of x is that. So you put it back here, and then you integrate. Okay. Remember, you have to do this integration. So please remember how to do those integrations. So keep them at your hand. Don't forget that. Now, if you want to find, how much is the deformation going to be at this location, at A, because of this torque given here, what is going to be the twist there? Now, by deformation, I mean twist, okay, for a member under torsion. Phi of A is going to be du by dTA, right? Now, TA is a point load, so I don't have to change anything. It's an existing point load, and therefore I can just take a derivative with respect to this, and that will give me my phi at A. Okay, again, this is based on Castigliano's theorem. Castigliano's second theorem. All right, is that clear?